I'm going to just write this as a whiteboard. I have some just slides because I can't draw. I was born with 2 left hands and I'm right-handed, so it's a challenge. The first lecture is going to be introductory material that has been known for a long time to prepare for the second lecture. We're going to tell about new things. If the first lecture is too slow, let me know. It's always easy to speed up. Okay. All right. So if you want to take some references, so as I said, this first part, there are excellent reviews and introductory papers. This paper by Zegers is really, really good. If you want to learn a little more about phenomenological superconductivity. I'm going to tomorrow be talking a little bit about vestigial orders, and this is a review that we wrote recently. And then tomorrow we get to results that we did in these papers, okay? All right, so let's get to work. And my understanding is that there will be an exam tonight, right? So I urge you to pay attention. Okay, so I'll start by why multi-component superconductivity. So let's start with the basics, and I'll tell you that multi-component superconductivity is unavoidable. So let me know, is this big enough, or is this? Yeah. Okay, so when we write down the gap function, we really should write this as a matrix, because if I think of the pair C dagger K alpha, C dagger minus K beta, nothing tells me what the spins has to be. Okay? Now, again, let's start very basic here. What we know for sure is that if I change K to minus K and alpha beta to beta alpha, I'm going to put this as a matrix, so it's clear that this is a matrix in spin space. The anti-commutation relations of the fermions have to give me this result, okay? And then there are essentially 2 options, right? So one option is, and I'm going to assume that parity is a good quantum number, and so is spin, okay? So one option is that the function in momentum is even, so it's even in K. And then to satisfy this relationship, I have to be anti-symmetric in the spin, right? So how do we do that? Well, the easiest way is to, well, what do we do with 2 by 2 matrices? Well, we just write them in terms of Pauli matrices, right? That's what we do. So I can always write this delta alpha beta in some basis. And because of my extreme lack of creativity, I'm going to call delta also. Delta is going to be a lot of things. If I tell you what is this thing, just called delta, it's probably going to be right. But I'm going to write this in terms of Pauli matrices, okay? And goes from 0, x, y, z, right? So you see that in principle, I should have 4 different components of my gap. And you see where this is going, why I need this multi-component, okay? Now, if it's antisymmetric in spin, okay, so I want this to be antisymmetric in spin, which of the 4 Pauli matrices, I'm including the identity as Pauli matrix, which ones of them are antisymmetric? Andre? I don't know. Ah. So sigma y is the only matrix that is antisymmetric, right? So if I write sigma y, we do 0 minus I 0, okay? As the antisymmetric is the only one. So I know that among these 4 components that I have, only one works. Usually, you know, we lose the I, like Odin. No? Never mind. It's a Marvel reference for those watching on YouTube. So we take this I, we incorporate it back in delta, and then we just usually write, in this case, the delta alpha beta of K is just I can write delta of K, and then I do I sigma y because, well, there are reasons why we do that, but this is just more convenient. And now this complex function here has to be even in K. Okay? And this is the famous singlet superconductivity. Okay? Very good. So singlet superconductivity looks that you only need one component. I'll show that this is not true. But so far, so good. Any questions? Okay. So now, there's another option, of course, which is that this is odd in K, and then I have to be symmetric in spin. Okay? Now I have 3 Pauli matrices that are symmetric in spin, right? So you already see that in this case, I need 3 components of the gap. So delta, delta alpha beta has to be now, it's going to be a linear combination. I can write this as delta 0 sigma 0 plus delta x sigma x plus delta z sigma z. And these are all functions of k, right? So all these delta here are odd, right? This is fine, you can write like that, but there is a much more convenient notation. I'm just going to tell you what it is. So it is convenient to take that I sigma y in front of everyone. So you can write, you can just remember that sigma 0, I can write as I sigma y times I sigma y. That's trivial, with a minus, of course. Sigma x, I can also write as I sigma z, sigma y, and sigma z, I can write as minus I sigma x, sigma y. I have here my, just to make sure that okay. So then, if you just notice that, you can rewrite in this notation, which is the Balen-Wertheimer notation, which is much more used, which you call this then a delta, which is a vector dot sigma I sigma y, okay? So you see that this delta vector is trivially related to delta 0, delta x, and delta z, okay? And again, this is a very convenient notation, and that's what everything here, alpha, beta, okay? And now delta of k is an odd function. It's minus delta of k. And this is the triplet superconductor, okay? So the first lesson we learned from this very simple exercise is that any triplet superconductor, again, if I have spin rotation invariance, which you never have in real life, well, sometimes maybe, and parity, which you almost have always in real life, has to have 3 components, okay? Any questions? Yes?
I think it should be delta minus k on the right-hand side.
What did you say, Oscar? Sorry.
Never mind.
Yeah. Thanks, Oscar. All right. I knew I was setting up myself here. Okay, now this seems okay. Well, so as long as I look at singlet, I don't need to worry about multi-component superconductivity, but that's actually not true at all. So let's look back a little bit in the singlet, and I'm going to look at the linearized gap equation, okay? And you've seen this equation here many times. I'm going to look for a singlet. You can do the same for triplet. Let's just do simpler for singlet. You have, I don't know why I keep putting this vector here. Delta of k is sum over k prime. Again, I already took care of the antisymmetry in the spin. There is a pair interaction that depends on v k k prime, delta k prime. And I have here tangent hyperbolic of beta epsilon k prime over 2 epsilon k prime. Okay, so this is just the gap equation. And I want to take a closer look at it, okay? Now, I want to solve it, but I want to solve it in the minimal possible assumption. So what is usually when you say I'm a physicist, you use, and people say, oh, you do approximations. What's the first approximation that they tell people you do? No, much simpler. Spherical cow. No? You treat a cow as a sphere, you don't know the joke? You do. So let's treat this as a spherical cow. In the sense that I'm going to assume that I'm in isotropic space. Okay? So if I'm in isotropic space, I can expand my delta in a basis. And this basis is very known. It's just the spherical harmonics. Right? So I'm going to call this coefficient CLM. And then I have the spherical harmonics. Now, I'm making one assumption that I need to be a little more careful about. I'm going to assume that my gap only depends actually on the direction of the moment, so that the magnitude is always at kf. Okay? But that's fine, because in the end, I have this factor here that will essentially ensure that this is true in BCS theory. Andre mentioned that in Eliashberg this is also the case, but in principle you can extend that and have a gap function that depends on the magnitude of the momentum. This is usually relevant if you have very dilute systems, but we're not going to talk about this here, okay? All right, so that's great. Oops. Okay, so now I can also, if I have spherical symmetry, or if I in isotropic space, my pair interaction, I have to be able to write this as sum over harmonics, like this, okay? It can only depend on the coefficient L, okay, because of the spherical symmetry that I'm assuming, okay? And I can now plug this in, okay? And again, I'm assuming that all that matters for my pair interaction is that it depends on momentum, and as function of momentum, it has a cutoff that you can call the bi-frequency, or you're just going to call a cutoff lambda, okay? So then what I get? I'll get, if I substitute it in this equation, I get delta of k is going to be some, I'm going to do here k hat. I'm just being very, very, I mean, you can go to prison for doing this kind of notation in some mathematics departments, but I'll take my chances. It's just sum over momentum, okay? But the directions. So then I have here sum over L and M, and I need also L prime and the M prime. For the momentum, I get VL at Y L M K, Y L M K prime. Now times C L prime M prime del, oops, Y L prime M prime K prime. And then now I'm going to do an integral over the energy. So I separated angle and energy. Okay? And I have to, of course, then multiply by the density of states. Okay? That's called rho f, tangent hyperbolic of beta epsilon over 2 epsilon from 0 to my cutoff, which you can think in electron phono is the bi-frequency, otherwise just call it, yes?
No sum over L and M, only over L prime and M prime.
No, I have here, sorry, I have this one. Here, from the V.
Oh, I see. Sorry.
Yeah, no problem. I'm not going to take points out of your grade. Sorry. Okay, good. So now, okay, this integral here is, you know, you learned this before, right? And Andre gave when he showed this is just the Cooper logarithm, so you get log of 1.13 lambda over TC, okay? Again, I'm linearizing the gap equation. And I can do the sum over K prime, so this was K prime. Sum over K prime, and again, this is really an integral, but that's okay. L prime M prime is going to be, K prime is going to be delta L prime, delta M prime. So now I get the delta K is going to be sum over L, M, okay? Now I'm going to do this, VL rho f log of 1.13 lambda over TC, and now here CLM Y LM of K. Okay, this is an eigenvalue problem, right? And what I need to solve it is to find when this guy here is 1, okay? When this, remember, because delta K is, this is exactly, right, delta K. Well, you see that this only depends on L. So I can look at different angular momentum sectors independently, and I can find for each angular momentum, TCL, is just going to be the BCS formula here, e to the minus 1 over VL rho f. By the way, I made an assumption here that this V is attractive. So from the beginning, This is V negative. And again, it could be in different channels. So remember when Andre mentioned, Professor Chubukov mentioned that you can have something that is repulsive interaction, but no, serious, something is repulsive interaction, but when you project on a certain angular momentum, it effectively is attractive. This is VL, okay? So in this notation, VL positive means attractive in that channel. The interaction itself may be repulsive, okay? But anyway, but this you see, for each L, I'm gonna have a TC. Actually, again, going back to Andre's talk, remember that when you did the Kohn-Luttinger, you found instabilities in different L's. That's just one mechanism here. But the key point that you find is that it depends only on L, not on M. So what I find actually is that delta K is sum over M, and now the CLM for that fixed L, I'm just going to call delta M. It doesn't depend now, it's just a number, it doesn't, or it's a function of K. It's just a complex number, YLMK, for that particular L channel, okay? And of course, M goes from minus L to L. So what this very simple lesson teaches us? Yes?
Just a quick question. So if the interaction is repulsive, what is the condition for the projection to a particular channel?
You can do that for any channel, but there's an assumption here that this VL is positive. If VL is not positive, there's no solution to this eigenvalue equation. And I just want, my VL here is just the minus the original interaction. So VL positive here means attractive in that channel. It's just a notation. I could have put a minus in. You know. So okay, so what do you learn from this very simple spherical cow exercise? What we learn is that, well, let's see. What does the L really mean? L means different superconducting channels, right? L equals 0 is, now we're going to borrow the language from orbital atomic physics. We call S wave. L equals 2 is D wave. L equals 4 is going to be I wave, and so on, okay? I skipped the 1 and 3 because these are odd parity. They have to be solved in the triplet channel, but you can do the same, okay? But what do you find is that this is what we call conventional superconductors. Now, I'll be a bit careful to say that you could have unconventional superconductors that are also L equals 0, for example, S plus minus, but for simplicity here, let's just talk about this. And L equals 0, of course, what we find is that for a given channel L, the number of gap functions, each gap function is 2 components because it's complex, is 2L plus 1. Okay? Which means that any unconventional superconductor has to have more than one component. That's the lesson we learned. If you did that this is for singlet, okay? This is for singlet. If you did the same exercise for triplet, then you multiply by 3 because remember I had those 3 from before. So you get 3 times 2L plus 1. Again, this is the number of gap functions. The number of free parameters you still multiply by 2 because this is complex. Okay? So you see the only gap function that is not multi-component is S wave. Everything else will have more than one component. Okay? So in particular, if you do helium-3, which is a superfluid, it's actually L equals 1. There will be 9 gaps times 2. There are 18 parameters. And that was a problem that people back when superfluid helium was discovered were trying, like Tony Leggett in his papers, trying to find different solutions and so on, okay? Great, so I just explained to you why we need why, it's not that you need, it's gonna happen, multi-component superconductors. Yes?
Isn't L equal 4 called G wave?
Yes. No, wait, yes, that's right. L equals 6 is I wave. You are right. Thank you. Then, yeah, this is borrowed from orbitals, and I just learned up to 5F, so F electrons, so I forget after that. Thank you. This is great. Now let me ask you a question. Do you know of any, let's look at L equals 2. We're going to focus all these lectures on L equals 2, although a lot of this works for other cases, okay? So I have 5 components, so any D-wave superconductor, I need 5 components. And you can do in terms of the index m, but a little bit more intuitive, we use instead of the spherical harmonics, just the cubic harmonics, just because a little more intuitive. So the 5 components are d, delta, I'm going to call 3z squared minus r squared, dx, oops, I'm not going to use the d, x squared minus y squared, xy, xz, yz, okay? So I need these 5 components to describe D-wave superconductors. Question to you, have you heard of any D-wave superconductor? Cuprates. How many gaps people use to describe the cuprates? 5?
But there the symmetry group is also not full rotational symmetry.
Yeah, that's exactly where I want to go. Exactly. It's just one. Why? Why usually, actually, most of the times we don't need to worry about the multi-component nature. It's because of the spherical cow. Meaning, it's because in reality, things happen in a crystal. Superfluid helium is a little bit separate because of that, it's special. But if you put things on a crystal, you no longer have this rotational symmetry. And these 5 components will split, okay? So, and that's the reason why when you go to real materials, only certain cases you're going to see multi-component, okay? So, so in crystals, there's something called the crystallographic restriction theorem. Restriction theorem that says that I can only have rotations that are twofold, or of course one is trivial, 1, 2, 3, 4, and 6. I can't have arbitrary rotations. Okay? And that's going to make these assumptions different. And then what you have to do, instead of thinking of SO3, which is the group of rotations, you have to now think in terms of so-called point groups, which are discrete groups, okay? And now you have to classify according to these point groups. And you know that because you studied, there's the same physics when you have the orbital states in a crystal, right? So for example, let's do a few examples here, right? So if I have a cubic system, okay, these 3 components here, I'm just going to call I'm going to just call this. They split in 2. There's one that is d 3z squared minus r squared, dx squared minus y squared, and dxz, dyz, delta yz, and delta xy, okay? These go by the name T2G, EG, because it's the irreducible representation of the group, or T2G, which you may have heard in orbitals, okay? But see, if you have a cubic D-wave superconductor, necessarily it has to be multi-component, okay? If you do now for a hexagonal system, which is what we're going to focus later, now the splitting here of these 5 components, they're actually just, one of them transforms trivially, so it's not actually a D-wave formally, but you also get 2 components. One is dx squared minus y squared, the delta xy, and the other one is xz, yz. This goes by the name E2G and E1G, but it doesn't matter, these are just names. Also in a hexagonal system, if you have D-wave superconductivity, it's going to be multi-component. And that, now you see why this kind of topic appeared back when we talk about twisted bilayer graphene and other more systems, because they're hexagonal, and there are theories where they are D-wave and so on, okay? And now, just for completeness, in the tetragonal case, which is where most of the discussion was dominated over the years because of cuprates, of course, then we split into 3 possibilities. One is dxz, dyz. the other is x squared minus y squared, and the other is xy. This here is our cuprate friend. Okay? And that's why, in that case, you don't need to worry about that. Now, for example, there are theories that in the rutheniates, this guy here becomes is one of the gap states. I know, and this is just to give you a taste how these things can be interesting. I think Marcel Franz in his lecture is going to talk about twisted cuprates. And it turns out that if you take two tetragonal lattices, twist them by 45 degrees, the resulting group is not really tetragonal. It's a non-crystallograph, is a quasi-crystal. And then these two guys here, these two guys now transform as the same thing in this twisted. And that's why you get these D plus ID states and whatnot. Okay? Just to make a connection with a lecture that will come later. Questions? Yes?
When you're talking about splitting of these orbitals, are they splitting in the sense of energy splitting, or is there?
They will have different transition. There's no reason why they would have the same transition temperature. That's the reason. I mean, they could be coincidentally that they have. Sure, that's a fine tuning. But when I'm putting like this, what I'm saying is that these two gap functions have to, the symmetry forces them to have the same transition temperature. So what I'm referring to multi-component superconductivity is this, is when there's a superconductor that because of symmetry has to have more than one gap function. There are other things you could do. You could have multi-band superconductivity and you can interpret that in terms of multi-components. I'm not doing that here. Or you can have two different gaps that have no symmetry reason to have the same transition, but for fine tuning they have. I'm not talking about them either. There was a hand there, yes?
So if you're just doing a transport measurement, would you only ever be able to see the largest gap of all these functions, or do you still resolve all of the separate?
We'll talk about it very soon. How, because there are two, but how are they combined? We're going to exactly solve the problem now and show what are the possibilities. It turns out that with transport, you can see, you could be able to see more than one. Yes?
Can you have multi-component superconductivity in 1D from this analysis?
Well, whether it's one, well, yeah, 1D is tricky because the world in 1D is kind of tricky. I don't think so, but you could have a 1D where, let's say they have a 1D system that doesn't have spin orbit coupling. And then if you have a triplet superconductor there, there are going to be 3 components, for example. So you can have it. Just so you know, for group theory enthusiasts, SO3 is a non-abelian group. Point groups can be abelian or non-abelian. Only non-abelian point groups have multi-components, multi-dimensional reduced presentations, which are multi-component superconductors. So I'll mention this later. Nick told us about uranium telluride. The point group there is orthorhombic, which is actually it is abelian. So any multi-component superconductor, as he was mentioning, has to be coincidental. It can't be enforced by symmetry. Okay? All right, any questions? Okay, so this was the introduction to tell you why we need to have multi-component superconductors. Now I'm going to work out in lots of details one example. The example I'm going to give is exactly the hexagonal case for D-wave. It actually, the same works for a lot of other cases, but I want to do one of them, all the dirty details, okay? So hexagonal D-wave, which is the one that has 2 gaps, delta x squared minus y squared and delta xy, which from now on I'm just going to call delta 1, delta 2, okay? And that's what I'm going to refer to, all right? Okay, so I'm not talking about the mechanisms. You heard from Andre what there could be different mechanisms from Aries and his talk. I'm just going to say there's a mechanism, okay? And I want to know what are the properties of this multi-component superconductor. So I can do a mean field decoupling of my Hamiltonian, okay? And simply write this as the usual stuff, right? This is sigma, C dagger, K sigma, CK sigma. And now I need to introduce the 2 gaps. Now, one of them, the delta 1, you see, I have to be careful how I couple it to the electrons. There is this x squared minus y squared form factor. It means that I need to couple it to a cosine of 2 theta, the angle. I'm going to put a k here so you know this is the angle of the around the Fermi surface, if you wish. And I also have to do the same for delta 2. Delta 2 is xy, so the coupling here is sine 2 theta, c dagger k c k. Okay. So this is the mean field Hamiltonian for this d-wave superconductor in the hexagonal lattice. And you can now go ahead and just calculate things the way you would. Oh, of course, there's the complex conjugate.
So should it be C dagger, C dagger, C dagger, C dagger?
Oh, I'm sorry. Yes, thank you. Thank you. Okay. All right. Now you can solve the problem, diagonalize it the usual way. You're going to find 2 levels or 2 energy bands that are particle hole symmetric, plus minus square root of epsilon k squared. I'm going to start dropping the vector notation on k just because I want to. So, sorry. Plus absolute value of delta 1 cosine 2 theta plus delta 2 sine 2 theta squared. Okay, so that goes back to the question, how do I measure this? Well, you already see that the energy spectrum depends on what delta 1 and delta 2 is, right? Oh, how do I know what they can be? If you go back to the degeneracy that I showed, comes from the linearized gap equation. In principle, what I should do is solve the nonlinear gap equation, and then I will find what is the relative values of them. This is very messy. There is a simpler way, or a more intuitive way, which is to look instead. Oh, what did I do here? Okay. Sorry. Suddenly became much thicker.
It's more important.
It's more important, that's true. Okay. All right. Okay, so it's much. Okay, that is just becoming a little bit.
-5 points.
Okay. Yeah. Well, maybe that's what is going to happen, and that's how it's going to be from now on. Okay. Yeah. Whatever. Okay. So we need to look at the free energy. Yeah, I don't know what I managed to do here. Yeah, I don't know. Okay, so I'm going to look at the free energy. This is bothering me so much, you have no idea. I mean, this is really impossible.
We read boldface.
Huh?
We can read boldface.
But I can't. No, I'm joking. Okay. Almost done. No, I don't want this option. See, I knew this was going to happen. You have no idea. You can't see what I'm trying to do here, but it's not good. It is not good at all. Okay. All right. Free energy. All right. So this free energy, what you can expand in a free energy, and of course, you know, if you look at this into quadratic order, they're degenerate, so they have the same quadratic term. Remember, A here is some t minus tc, right? So when A is negative, tc will go below tc. There's a quadratic term. There's one very easy quadratic term that has to be there, which is just the same term but square, okay? And you see that these terms here, if I write the free energy like this, it looks that I have an additional symmetry that is not present in the model, right? It means that I can do any rotation within this 4-dimensional space, right? But that's not true. And in fact, there are 2 different ways. You can use group theory, or you can do a microscopic calculation. you find there's going to be, for the hexagonal system, a new term that I'm going to call G, which I'm going to call here delta 1, delta 2 star, minus delta 1 star, delta 2, absolute value squared. And this term now is going to be essential because it's going to tell me what are the combinations of delta 1 and delta 2 that I can have. Okay? So what I'm going to do for the rest of the lecture is solve this problem within mean field. And then tomorrow, we're going to do beyond mean field to see what happens. Okay? So mean field solution. So I'm going to do this here. And within mean field, all I need to do is minimize this, right? And I can do that, it's fine. There's a more convenient parameterization of this gap. I can call this delta bar. It keeps changing this is really upsetting. I'm going to write to Apple. They're not going to care. Delta 1, delta 2. I'm going to, instead of writing in terms of 4 components, I'm going to write in terms of a global magnitude and a global phase, and relative magnitude and relative phase. It's just going to make life a little bit easier. So global magnitude, which I'm going to call delta. Global phase, which I'm going to call theta. And now, I'm going to, the relative magnitude, I'm going to use alpha. Alpha is just, again, how much of delta 1, how much of delta 2 I have. A relative phase, what did I call? Beta, I believe, sine of alpha. Just make sure that I use the same notation in my notes. Yes, okay? So that's great. So now, this parameterization is actually much more convenient because I know, for example, that this here comes from the global U1 symmetry, and that's not going to appear in the free energy, right? So if you just substitute it there, what you're going to find for F is going to be A over 2 mod delta square plus U over 4 mod delta 4, which again is the same as what you'd get for a standard single component superconductor. But now we're going to get G over 4 delta 4. And if you do this combination here, what you're going to get is sine square 2 alpha sine square beta. Okay? And this here is the free energy that we will solve now. Any questions? Okay, so now it's easy, and you see in this parameterization here is very easy what we need to do. I'm not even going to write it here because you can immediately see what's going to happen, right? So so we have 2 options for G, right? If G is positive, what minimizes? Let's actually start with G negative first. If G is negative, which value of beta do I need to have to minimize this free energy? Pi over 2. But could be plus or minus. Right? So this is the solution. What about alpha? Again, if I want to maximize this term because G is negative, right, if you wish. And I maximize it by doing beta equals plus or minus pi over 2, and alpha equals pi over 4. Okay? That is the highest value you can have. And that's the solution. Okay? What does it mean? Well, let me write this now. I'm going to get that my delta, I'm going to write delta bar, delta 1, delta 2. I told you there will be many deltas here. That's going to be a magnitude, which I need to solve the Landau equations, e to the I theta. There's going to be now a square root of 2 coming from sine and cosine, but it's going to be 1 plus or minus I. Okay? All right. So, and of course, if I substitute it back, I would get my free energy. It's trivial to solve now because you get plus U plus G over 4 delta 4. And you can just solve it to find delta. Okay? But I'm not interested in delta. Okay, so what is this state? So you have a global phase, right, which that's a spontaneous symmetry breaking. That's the U1 symmetry breaking. But what about this plus or minus I? I have 2 different, besides the phase that I have to fix, I need to choose this relative phase between the the two gaps to be plus or minus pi over 2. Okay? There's an addition of symmetry here being broken. What is this symmetry? So let me ask you this. What happens if I do delta, oops.
Six-fold rotation?
Let's see if it has six-fold rotation. So I'm going to go back to my energy, right? Which was square root of epsilon k squared plus delta 1 cosine 2 theta, oops, plus delta 2 sine 2 theta square, okay? This is theta k. If I substitute this here, see, delta 1 is, the e to the I theta goes away, and they have a relative phase of pi over 2, so the gap actually is going to be plus or minus square root of epsilon k squared plus mod delta square over 2. It looks exactly like an isotropic gap. So it doesn't break any of the rotational symmetries of the problem. So what symmetry is this plus or minus I breaking? Anyone wants to give it a try?
Time reversal would be broken, right?
Time reversal symmetry. How do we know that? Because if I take this delta and I take the complex conjugate, right? I'm going to get delta over square root of 2 e to the minus I theta 1 minus plus I, right? This one here, this guy here, I can always undo with a gauge transformation. So that's not a problem. But this one here, I can't undo. So delta star and delta differ by more than a gauge rotation, which means that I break time reversal symmetry. So this is what we call a chiral superconductor. Okay? Let me go a little bit deeper in understanding why do we call it chiral. If I call it chiral, what does the name chiral remind you of? Something that has angular momentum, right? What is the angular momentum here? So it turns out, and that's going to be very important tomorrow, I can write down this combination here, delta 1 star, delta 2, minus delta 1, delta 2 star. I can do an I here, because then it's real. Just make sure I use the same notation here. Yes. If I just substitute what I had here, I'm going to get delta, what did I do? Okay. I'm going to get delta square, okay? Sine beta, or sine 2 alpha, sine beta, okay? Now alpha is pi over 4, okay? So this is just delta square sine of beta. And now you see that this can have two values, right? Plus delta square if beta is pi over 2, minus delta square if it's minus pi over 2. This object here is quadratic. Is quadratic in the gap, and it actually has the same transformation properties as an angular momentum along the z direction. I'm not going to prove it here. Just believe me, it's true. It's going to be so important that we need to give a name to that. Why don't you choose a letter? Or you're going to call it Paul. I don't know. Just choose a letter. Psi, great. I also need an index. 2, great. Psi 2. It's going to be, the 2 is going to be extremely important, I promise. It's not me just playing a trick at all. Okay. So, but the point is that this psi 2 looks like an order parameter, but it's quadratic in the gap. But this is an angular momentum, okay? So this transforms as Lz, and that's why we call this a chiral superconductor. Okay. Yes?
Yeah, so time reversal is definitely broken, but even, so this is like the D6H, I guess, the group.
It could, yeah, could be.
So does it also not break like the in-plane mirrors? Because in-plane mirrors, e to the I theta will go to e to the minus I theta, right?
The gap transforms non-trivially. You're correct. But if I look at the resulting space point group after this condenses, is still D6H because of the gauge invariance. So delta transforms non-trivially under U1. So
Yeah.
it is still, it does not break any of the six-fold rotational symmetry of the lattice.
That's okay, but
Yeah.
I'm talking about the in-plane mirrors.
It does not either. The point group is the same, it's D6H.
Even after condensation?
Even after condensation. And I'll go back to that a bit later.
Okay.
Think of a D-wave cuprate superconductor.
So you were telling me D plus IT would not break in plane wave. This is D plus IT.
Yes. Yeah.
He's asking simple question. Change x to minus x.
Yeah.
It's the same.
I goes to minus x.
X to minus x?
Sure, because one component is dxy. Prime x.
No, sure.
X to minus x, you change
But
y to minus I to minus
I think we're talking about different things. I'm talking about delta itself transforms non-trivially under mirror, under rotation, because it transforms as the E to D irreducible presentation. I agree with that. What I'm saying is that once it condenses,
This particular combination, right? That's what I'm asking.
the gap function does not break any of the six-fold rotational symmetry because
The rotation is fine, I agree.
yeah,
But
or mirror or anything because it's mod delta square that appears. We can talk more later maybe.
yeah, no,
Uh,
that's all right.
Like an angular momentum, it goes to minus under mirror.
Huh?
It's just like angular momentum,
Yeah.
no? It goes to minus itself under
In plane wave, that's right.
yes. So
I guess maybe I'm a bit confused with what we can talk more later, and I need to maybe understand. You're talking about the mirror that is the
Sorry, out of sorry.
vertical plane.
Vertical, sorry.
oh
Yes.
because there is an angular momentum.
Yeah.
You can't have any mirror that is vertical. You can only have horizontal mirrors. So
Yeah, so it was
okay, that's what. Okay, fine. Sorry, you're absolutely right. Okay. Now let's look at the second case where G was negative, is positive. I'm sorry. Now that term, I'm just going to write down. Let's just write down again the whole free energy. It was A over 2 delta square plus U over 4 delta 4 plus G over 4 delta 4, I'm sorry, sine square 2 alpha sine square beta. Okay. So if G is positive, I minimize this by doing what? By setting beta to 0. Okay? And then alpha can be anything, because I already minimized that term. I'll come back to this point of alpha being anything. But let's look at what this means for my gap now. So let's again look at the energy. Now I have again epsilon x squared, k squared, plus, remember, delta 1 cosine 2 theta plus delta 2 sine 2 theta square, right? Now, again, remember, my delta now, which is delta 1, delta 2, is going to be mod delta e to the I theta, and now it's just cosine alpha, sine alpha. Alpha is in the undetermined, but the relative phase is now 0, okay? I'm defining the phase between minus pi over 2 and pi over 2, so I don't need to worry about that. So now if I do that, well, you can work this out, and what you're going to find is that I have this guy plus mod delta square. What you're going to get here is a cosine square. Sorry, this should be theta k here. 2 theta k minus alpha. Minus 2 alpha, I'm sorry. Okay? No, alpha. Yes. Okay? What is this equation here? What does this describe? Describe an ellipse rotated by alpha, right? So my gap function is now, think of this, I had a system that had 6-fold rotation, but now it looks like an ellipse rotated by some angle. This is going to break the symmetry. Which symmetry? The rotational symmetry. So this breaks rotational symmetry. I started at 11:30, right? Show you. Thank you. How much time do I have? I forget.
10, 12 minutes.
Oh, that's eternity. Great. It breaks rotational symmetry. Because of this, we call it a nematic superconductor. Okay? Okay. I have pictures. I said. Here. See, I actually prepared it. This here is what the nematic gap looks like. Beta is 0. You see here that my alpha has some values. I'll go back to this point, okay? But you see that the gap here, just plotting the gap around the Fermi surface, okay? And you see here that it's twofold symmetric, not sixfold, okay? This is the chiral gap. So you now clearly see that it still has sixfold symmetry, and beta is plus or minus pi over 2, okay? All right? So in fact, you can see from this equation, from this equation here, that this here vanishes when alpha, or when 2 theta q is alpha, right? So these are called nodes. So these are the nodes of the superconducting state. So this is more similar to the D wave of the cuprates because there will be nodes, meaning there will be points where the spectrum is gapless. Sorry, what are you guys talking about? Sorry, I'm joking. Thank you. Yeah, it's pi over 2. Okay? So there'll be nodes, and that's exactly when I showed you here this picture, you could see these nodes here, right? So it's very similar to the cuprates. That this, in fact, you could even interpret that as you see that the cuprates is alpha equals 0. That gives you the same. But this is a sixfold rotational symmetry. And unlike the cuprates, the gap doesn't break the fourfold rotation because alpha is 0. Here, alpha is not going to be 0, and you have threefold rotation. So you break that, okay? Any questions? Should we talk a bit about why we call it nematic? Should we do it? No? Let's do it.
Can you remind what was G, because it was so central?
Which was what?
G, the definition of G, because it...
Oh, yes. Very good point. Yes. So this G came from my free energy here, right? So it's a Landau coefficient.
Yeah, but if you can go further back...
Oh, this is the first time...
Give it to us. It's one of the Landau.
Right. So if I just do phenomenology, I don't know what is G. Could be positive or negative. Now, I can derive it from a microscopic Hamiltonian. For example, I have this Hamiltonian here, right? I could, in principle, do a Hertz-Mills kind of approximation. Just integrate out the electrons and get a free energy in terms of delta 1 and delta 2. In weak coupling, this G is positive then. It's just some derivative of density of state, something like that. But there are models where they can be negative. But this is model dependent. For example, Andre has a paper on the nematics, the superconductivity in TBG, and I think you found regions where this G was negative, no? Oh, no, this was not you. I'm sorry. This was Liang Fu and Jorn Vanderbos. I'm sorry, I confused. That they showed that it's always positive, but if you couple to some systems, it can be negative.
Yeah, you need extra coupling.
Yeah, you need extra coupling. So weak coupling is always positive. It always gives chiral. People say, oh, it's because it fully gaps the Fermi surface. That's not true because, again, it's not a quadratic level consideration. It's the non-linear gap equation, okay? But there are models where it's going to be negative. Yes?
You could have also chosen alpha to be 0 and beta to be 3, is that correct? Or that would be the same thing?
That's going to be a problem once I include an next order term. To some extent, sure, you could put beta to be anything and alpha to be 0, but as I'll show you, there is a 6th order term that's going to fix the alpha, and that would not work. Okay? All right. So why do I call this a nematic superconductor? It's because of the following. I can define, oops. Just do a very quick, this is going to be the last point here. I can define this two-component object that is delta 1 square minus delta 2 square, delta 1 delta 2 star plus delta 1 star delta 2. If it all looks ad hoc, it is. I'll go back to this and just explain where this comes from. I'll need a name for that. I'm going to call this psi 3 and psi 1. Again, it's going to be important later. But for now, I just call it is because I can call it whatever I want. I created it. Sorry, it's not really true. someone else call it. But okay, but if I write this here, what you get here is that you're going to get delta square. This is going to give me cosine 2 alpha, okay? And this is going to give me sine 2 alpha cosine beta, okay? And if I fix beta to be 0, right, then I get delta square cosine 2 alpha sine 2 alpha. So this object, which is a real two-component vector that has this structure, is precisely transformed as a nematic order parameter. I'll explain you why, but this is the thing I wanted to tell very quickly, why. And that's why this is the same way that I had something that psi 2 in the chiral case transforms as an angular momentum, this here transforms as a charged quadrupolar density, which is nematic. Let me briefly tell you, let me do a different box here. Let's do here. Just to tell you very quickly why. Let's go back. Just nematic comes from liquid crystals, okay? Do you know what the nematic phase in liquid crystals is? So I should have a picture, but I don't. I'm just going to try to draw. In nematic, you have this, pretended these are cylinders, cylindrical molecules, okay? And you put them together. You can put them so that on average, they point in the same direction, but their center of mass is completely random. This is a nematic phase. You think of putting a collection of cylindrical molecules. If they point in the same direction, but their center of mass is anywhere they want, they don't break translation invariance. So in that regard, they are liquid, but they choose a certain orientation. In that regard, they're solid. They're a crystal, and that's why it's called a liquid crystal, okay? So a liquid crystal is defined by a vector that has 2 arrows or a vector that has no arrows, however you want to think of it. But I can define in terms of why do I need something that is an arrowless vector? Because these are cylinders, right? So if I rotate it, it looks exactly the same by pi. A vector doesn't have this property, right? So if you want to create an order parameter, these again all liquid crystals, if you want to create a property, an order parameter, so I have the direction d, it's called this the director. It's a vector and tells me the direction. That's not a good order parameter because if I rotate by pi, it goes to minus itself. So the object that you have to create is actually a rank 2 symmetric traceless tensor in 2 dimensions, which is what I'm going to do. This tensor goes qij is just 2 di dj. They are the components of the vector, so this is just dx dy minus d squared delta ij. Okay, that's by construction an order parameter that if you rotate by pi, it remains invariant, and if it condenses, it breaks rotational symmetry. And how is this connected to what I wrote before? Well, just write this in matrix form. This gives me dx squared minus dy squared. This gives me 2 dx dy, 2 dx dy, dy squared minus dx squared. Okay, I'm just writing the 3 independent components. You see trace is 0, it's symmetric. And I can think of this actually, if I write in terms of Pauli matrices, as dx squared minus dy squared, some Pauli matrix tau z, plus 2 dx dy, Pauli matrix tau x. So in this pseudo-spin space, I can define an order parameter I'm going to call phi, which has 2 components, dx squared minus dy squared, and 2 dx dy. Again, this lives in the pseudo-spin representation, which is nothing but d squared cosine 2 alpha sine 2 alpha. This is the order parameter for a standard classical nematic liquid crystal in 2D. Now, if I go back to what I wrote here, you see the exact same structure. There's no cylinders or anything. This is the gap function that is behaving as this nematogen, if you wish, and this the relative amplitude of the two gaps, delta 1 and delta 2, acts as the nematic director. Okay? All right. Should we have lunch? Should we have questions before lunch?
Two things. So
Yes. Oh.